So Tim Conway has been a professional in the ICS security industry for quite some time, starting out his days at NIPSCO on the grid operations side and as the electric grid operator and manager of a lot of that, as well as all their NERC SIP training and reliability and organizational work before getting pulled over to work at SANS and be a course author for ICS 456, as well as just building out a lot of that we have here at SANS. The other beautiful thing about Tim that most people don't know is Tim does a lot of contracting work on the side for a lot of organizations. And it's not because he is looking for work. Unfortunately, Tim is one of those people that doesn't know how to say no to an important project. And so you will often find that some of our most important national projects on the topic of ICS will not list Tim Conway as a component of it, but they are core and critical. Tim Conway is core and critical to them. So he is one of those individuals, when the old Mr. Rogers quote of, find the helpers and look for those people. Tim is definitely one of those folks. Likewise, it is not too far from a stretch to say that if there was a twin to Tim's generosity and dedication to the ICS community, it would be Jeff. Jeff has spent 23 plus years before coming to SANS over at Rockwell, working with an amazing amount of companies around the community. And it's some of the coolest stories too, everything from just completely random manufacturing places to, oh yeah, no, here, and here I did this, and that made sure the plant didn't blow up. And like, that's nice, Jeff. Getting into, reliability and resilience long before we started talking about it as security. And then towards the end of his time at Rockwell, moving into the security side specifically. So I often love hearing Tim and Jeff talk. You'll see Jason Daly also jump on from kind of courseware development and kind of a research lab at SANS. And Jason will be, working on a circuit board while Jeff is coming up with logic, while Tim is explaining the operational impact. And in this mad, lab of scientists, in the end, our students benefit and they get to learn something more about our beautiful industrial world. So Jeff, Tim, we're extraordinarily excited to have you both at SANS. We're excited to have you for this talk. If you would, please take it away.
Thank you, Rob. That was a wonderful introduction and very, very unexpected. I appreciate the kind words. And yes, SANS, super exciting over the last couple of years where we've developed kind of a SANS Research and Operations Center where we've had this ability to help create labs for courseware and make them more real world and more practitioner focused, and bringing in people like Jeff and Jason, where we can build specific courseware labs with ICS focus, as well as kind of ranges for competitions and challenges and a number of other things. So one of the courses we got to build right away was ICS 612, which many have asked questions about throughout this conference, because many of you would have seen it last year kind of make its initial introduction to the world. And it's one of the courses that we were the most excited about. It's also one of those courses where we felt really, really strongly that if you became a pilot and you did a whole lot of time in simulators and you worked with kind of real world representations and data sets, and but you never actually sat in the cockpit, you never actually took off or landed an aircraft. It's one of those things where we felt in our courseware, in our curriculum, we really need a deep hands-on focused course. And ICS 612 was that. It came out kind of in March with about 70 to 75% hands-on labs and wiring and doing all kinds of things. And then the pandemic hit after we ran it once. So it's one of those courses that's really difficult to achieve the same learning objectives in a remote, virtual, kind of live online manner. So it's sort of in hibernation, while like many of us stuck in our caves around the world. We have had the opportunity to teach it in a couple of private runs and continue to do that for organizations where safety risks can be managed as much as possible and people aren't flying in from around the world to attend. But I can tell you the entire team that helped build that course is as anxious as the students are to take it back out on the road and start moving with it, because we know from it, we're going to build additional things that we're equally as excited about. So today, we're going to be talking about time and various time architectures. And with the time that we have left, kind of before this, this conference comes to a close and the summit comes to a close, we're really going to try to take what we have and spend more time on the industrial elements. So I'm going to move through the first couple of slides as rapidly as possible so Jeff can start talking and we can get into a demo element with the time that we have left. Jeff and I and Jason always try to do some level of demonstration on stage. That has gotten harder with our last few summits while we're remote in Asia Pac or in Houston and here. But so they're limited in scale. I think Rob mentioned the last one we did in person, we went through 6 or 7 attacks in 35 minutes. So you're not going to get that here. You'll get one brief demo, but here we go. So just a couple of things to talk about quickly, and then I will relinquish all time in the time presentation to Jeff. Just as we talk about kind of enterprise, and I'm being sort of careful with that word in regards to attendees here that are from an industrial control system or an OT perspective, you have to consider the breadth of assets that we're talking about, where you could, in the electric sector, you could have field substations with a tremendous amount of industrial control systems. You could have generating station environments with systems of systems and plant floor and all kinds of industrial control systems. But you also have control centers that have kind of that wide area state of view in a number of different infrastructures represented here. And they're not making megawatts. They're not stepping up, stepping down, routing it over kind of the transmission system, doing the substation switching work. They're a building with computers in it. And as you think about essential services at a plant or a field environment, the ins and outs, kind of the process needs for that plant to operate or that facility to operate, here kind of in these control center type environments or in these supervisory environments, some of those key inputs that you need to consider are things like time. And so while we say enterprise, and here's an example of kind of what a traditional enterprise, or even in some cases, some OT level kind of system time services look like, from primary domain controller or directory services or kind of LDAP or whatever your authentication model is as the primary time with secondary failovers, and pulling that kind of time source from an external feed. And then all of the local assets kind of being pointed to those primary and secondary time sources so that they can kind of sync up and be in a common time domain. As you look to a lot of network infrastructure devices from environment to environment, some of them may not have been configured for very good reasons to point to those time servers. And instead, they are also going out to external sources. So you have multiple pushes out of an environment to pull in an input that's very essential to operations. For kind of islanded or non-domained, more work group assets, many kind of configured and pointing to TikTok or kind of the NIST.gov or time.windows, and sort of looking at those traditional configurations that you may find in a lot of operational technology environments, and certainly within corporate business and enterprise. And as you look at the system accuracy needs and the time source needs, those are absolutely areas where you need to understand kind of what's being provided, what's being consumed, and what's the importance and sensitivity of it. So NTP v3, accurate 1 to 2 milliseconds in a LAN environment, tens of milliseconds in a WAN environment, and kind of looking at how some of these systems sync up, and looking at ntp.org and seeing, 90% of these NTP servers have network delays below 100 milliseconds, and almost 100% of them are synchronized within 1 second, which may seem like that's super fantastic. How does that even work? That effectively, that consistently, and function in that way? What may seem even more shocking is well, that's not good enough. When you're getting into real-time systems, to look at that and saying, that's not good enough for what we need. And that may be the case depending on the industry or the sector that you're in, and depending on what your telemetry looks like and your scan rates and kind of the sensitivity around your alarm systems and your process environment specifically. And if you have those kind of timing needs where you're looking at kind of synchrophaser data and time synchronization across relays, and you're looking at sequence of event data that's coming in, and you may need dedicated IRIG-B kind of time feeds. Those are all things that have to be considered. And if that's the sensitivity of your system, then you have to start thinking about what happens when there's failures. What happens when it's a misconfiguration? What happens when something doesn't communicate? What happens if it's an intentional misuse of a time forward, time back, and you start to move systems into synthetic time where they have to recalculate and make adjustments? These are all things that have to be considered from a misconfig, from a failure, from an unavailability, and from a misuse. You could look to the problems that could occur in just accessing data, accessing a system, because your credentials, your authentication system no longer functions due to time misconfigurations. You could look to incident response and problems with kind of sequencing when things occurred and the importance of those across forensics or auditing. You could look to operational data and sequence of events mismatch. A number of things have an absolute core reliance on time. And more importantly, as you get further and further down the Purdue model, it becomes a greater sensitivity of, especially if it's misused, if it's intentionally misoperated, and what the result can be. With that, I relinquish all time to Mr. Jeff Shear, so we can all start taking notes and learning from this this fine gentleman.
Thank you, Tim. I appreciate that. And I'll tell you, the first time I was one of the first few years I was at Rockwell, I went to a lunch and learn, and that ControlLogix platform had not even been around yet. A person was talking from our research center on small logic controllers, or SLCs, and it was a lunch and learn, and he was talking about his progress on getting time synchronized across a couple of them. And I was thinking to myself, well, wonder what he's going to do tomorrow, because that sure seems like an easy problem. And then you fast forward like 23 years, we were still working on time, getting time across different switches, across different controllers to be the same, to understand it, to timestamp it right and send it to higher level systems. And so what seems like was a casual brush of time seemed 20 years later to still be quite a science of studying time. So as Tim said, these are architectures that we've typically seen. So I've done a bunch of audits and a lot of time in the field. And what you end up finding is that people have guidelines, but they don't always implement them. And so one of the things that was written while I was at Rockwell was a converged plant-wide Ethernet document that we talked about how to push time across an industrial demilitarized zone. And again, for a refresher, the demilitarized zone, especially the industrial one, is to buffer traffic in and out of the enterprise zone or office space to an industrial side, so that the industrial side can continue to run and make products as you have some kind of disruption on the enterprise side. And so many times I found where NTP was being pushed through the IDMZ rather than being replicated, and there was a NTP server down in the industrial side that sent time, NTP time, to switches and to servers and to HMIs and to PLCs. As time has marched on, I keep overloading that word, as time has moved on, even things like PLCs can ask NTP servers for the time. And again, there's Windows 32 time, there's NTP time, and there's even more precision time that are required to make real-time industrial control systems run. So like Tim showing there, NTP will be directed through there. If you go ahead and hit the space button one more time. And then NTP will be synchronized from one source typically and kind of spread out through all of those industrial assets. Hit it one more time, Tim. So what happens is when we talk about a 1 or 2 millisecond precision on a local LAN, in most cases, that's okay. But when you're doing industrial controls, actual control systems, a lot of times it isn't precise enough. So when we had things like time not being shared very well, we would have these custom cards for applications like motion, or we'd create our own sequence of events cards that would have its own precision time, and it would go out externally and either get it from a GPS source or from a NTP source, and it would allow us then to do very accurate time measurements. And what we're going to find is that even today, there are packaging machines and sorters that have moved from event-based to time, basically time and predictive events, to know that something's going to happen. So if we're going to run a diverter or something like that, it's actually on a very frequent time. And we've done time advanced modules where I've done a diaper machine actually, and as you spread the glue on it, and as that line runs quicker, you need to actually do a timing advanced function to actually get the glue gun up and down and putting glue on something. So go ahead and hit it one more time. So NTP isn't accurate enough, but a lot of times NTP will be the source where the conversion of time to something more precise, like precision time protocol, will start its journey, and then clocks will be synchronized. And this assumes that you can have everybody participating in the network and the end devices being able to tell what kind of time delays or what kind of jitter was added as the timestamp moves along the network. Go ahead and hit the thing again one more time. So there is protocols like Precision Time Protocol, also known as IEEE 1588, that does start its life or starts its timestamp from NTP or GPS, and then is converted into this 1588 time, which gives you sub-microsecond range accuracy. And everything kind of starts with time. Like if we're doing accelerations or decelerations or velocity calculations, or if we're, heating soup up to a certain temperature, we're going to learn about when did we actually see a temperature actually start to change, or what's the time constants. And so lots of things start off of actually being able to do time. What's kind of interesting is embedded devices are the worst devices for keeping time. So we have compute resources on our desks that do a much better job of keeping accurate time. But embedded devices like PLCs, if you start reading different manufacturers, the time skew actually gets different as there's a temperature change. So if I'm cooler, I'm probably only going to lose maybe 3 minutes a month, whereas if it's really hot outside, I might lose actually or gain actually 4 minutes a month. And so what happens is in these different architectures, you'll have a time master. And again, that is a non-politically correct word these days, but the specs haven't caught up with our world today. But you'll have something that is considered the time source, and it will propagate that time out to other sources and say, hey, the new time is this time X, or you have to skew X plus 4 milliseconds or whatever. And so those times end up being skewed based on temperature. So all the factories are different temperatures. And then where we're going with this is that if I can affect that, the master of time, I can propagate that out to other resources and actually make them think it's the wrong time. And go ahead, Tim, and hit the slide. Yeah, NTP isn't accurate enough. One more time. One more time. So what does it actually mean, and why is time so important? If we're doing a critical process for an amount of time that's too short, let's say we're doing pasteurization, we're heating and allowing something to cool, and we're bringing those records back and say, yes, by golly, we did this pasteurization for 5 minutes, or we did it at this temperature for this amount of time. Or if we're moving a welding arm, or if we're doing package diversion or whatever, and we say, hey, at this particular time, we're going to do something, and our time is incorrect, then our whole control strategy kind of goes out the window. Over on the right-hand side, there's a mathematical formula that is very popular within, especially the United States. Other parts of the world use proportional, integral, and derivative control. With proportional control is just a multiplication of error. So as I get my error closer and closer, or my set point actual and my actual closer and closer together to where my error term goes to little or nothing, then the only thing that puts us to set point is this integral term, this integration of time. And so I've had real life cases in old controller platforms where they were running proportional, integral, and derivative control on a scan base, and the scan was longer and shorter and longer and shorter, and they couldn't get very good control. Having control platforms that have very accurate time measurements allows you to do very precise control. I kind of do this as a joke. Velocity, so if you're riding in your car and it says you're going 20 miles an hour, that is a distance over a time. So if you get pulled over and a police officer asks you, do you know how fast you were going? Tim Conway will give you $20 if you ask him, well, over what distance and over what time? So depending on the distance and time, if Tim and I were starting to run and we put 2 chalk lines on the road, and I ran there as fast as I could, and I stopped before the chalk line, and Tim was just jogging, and then we both crossed the line at the very same time, we would be going the same velocity over that distance, but just not over the same amount of time, or over the same amount of time. But I was going faster, and then I stopped, and then I moved. And so you can get a real skewing of velocity depending on how many times you sampled it over the time. So these things are very, very important. Also, one last point is that automation vendors would have never tried to overcome these timing issues if it wasn't important. So doing things like very accurate motion control, multi-armed, multi-movement moves to a very precise distance makes you have to understand time as in velocity, acceleration, and deceleration. So again, a problem that got solved because it's actually a very important problem. Go ahead, Tim, next slide. So using NTP is kind of the gist and the main focus of this particular talk. And the network time protocol has a special way to tell us that you are asking me too often what time it is. And so there, Windows time might ask like once every hour, but our little embedded devices might have to know way more frequently what is the current time. And so we can do something where we ask an NTP server, just like if I keep asking Tim Conway, hey, what time is it? Hey, what time is it? Hey, what time is it? Pretty soon he's going to tell me to kiss off. He's going to say, hey. So an NTP server has this thing called a kiss of death packet. And what happens is once I oversubscribe to this, then it's going to start sending me these kiss of death packets, which is not only filled in with the protocol or in the packet, in the data structure, it's going to say the word rate, but it's also, when I send it a timestamp, it's going to send me the very same timestamp back. So if I'm a smart client, I will start monitoring for this kiss of death packet if I could. This is our only indication that we've received this kiss of death packet. So there can be a lot of things that go wrong when I'm asking for time and assuming that it's actually doing what it's supposed to. So next slide. So if we look at a normal transmit, hey, I'm asking you for the time and I'm getting an actual response back that makes sense, is a lot of times an embedded device or other devices will ask the time, but in the timestamp, it'll stick like seconds from 1970, from January 1st, 1970, which is what in this particular demo, a Rockwell device will do. And then the response will come back in the bottom in the red box. You'll see where it actually fills in a time. So if I investigate that, I would want to know that my timestamp that I sent out is actually changed when it comes back as a response. An indicator that the kiss of death packet has occurred is that nothing would change. Now, I could have lots of things happen to that packet, or as a lot of people on this call could probably do some man in the middle and craft the attack and do things like that. But we're just going to show you what happens if you actually abuse an NTP server and not watch for the kiss of death packet to come back. So go ahead, next slide, please. So this is the kiss of death packet. So you're going to see that I had sent out the seconds from, there you go, one more time, I believe. I've sent out the indication that it's from 1970, and I look and I see the rate word come back and that the timestamps are exactly the same. So before we go on to the demo, go ahead and hit it one more time, I think. Yep, so I call this Back to the Future now. The magic of this is that I set up a PLC and I put a program in there that goes and asks an NTP server, and I peel that off, and I have, there is a register that is the basically the rollover time, and I've set that to the future to like 2036, so that we could have a laugh and say, hey, we're going back to the future. So with this said, let's go ahead and run the demo kind of quickly. This is a recorded demo. So what we're looking at, I don't know if it's running. Yep, there we go. So we're looking at this logic. I put in a special instruction to go do this, and I am online with this particular controller, and I'm communicating with it with just the standard RS Links package, and I'm looking at just a compact logic. And so there's nothing really special other than my logic. And this particular logic, I used an add-on instruction, and add-on instructions are made of logic and data, and we're just going to look at the data interface. And this data interface, I have a string where I point it to the address of the time server, which is .5.13. I'm looking at it once a minute, and I can force this thing to actually do an update. So if I go ahead and tell it to update and hit apply, then I get a done bit back. And so now I should be able to go and investigate what time it is on this particular controller. So I can show the controller. Again, this is just the properties of the PLC. I'm going to go over there to the date and time, and I'm going to see that that time actually matches the workstation time, and it's just the normal, you know, day, month, year, hour, minute, second kind of thing. And this is where I can manually set it. And we're going to show it later in the demo that it's being overwritten. It's also good to note that I can synchronize. I could become the time master and send this wrong time out to many other clients, which is done inside of a lot of industries. So if we were to look at a Wireshark packet, you're going to see where I'm sending out from the Allen Bradley PLC, the Rockwell at .2, I'm sending out the 1970, I'm sending out those seconds, and I'm going to see a response come back from that NTP server where it fills in the time. I'm not being rate limited at this point. I'm just showing that this is how it would normally work. Okay, so let's go look at the NTP server. So I just set up a Relic server as an NTP server, and hopefully it's still running. Yep, there we go. There it is. So we're going to see that there's 2 hosts. None of them are overrunning it, being rate limited. So the .2 is the particular PLC. So what I'm going to do is I'm going to go over here and start asking it quickly in about 6-second intervals. What is the time? What is the time? What is the time? What is the time? And so we'll go back here and we'll look at this, and we'll look at this from a perspective, and we see that under that R column, there's an L, and that is a rate limit. So now I should be seeing a kiss of death packet if I go to Wireshark and I start looking at this. And what I'm going to find is I'm still sending out the 1970 packet, seconds from January 1st, 1970. And here I will investigate. Let me click on the right thing. And right there, I see the kiss of death packet, the rate. So I see that it is actually sending me the rate. Let's go see what the controller thinks the time is currently. So if I go back to the date and the time, I see that it's 2/7 of 2036. Again, that's the rollover date that I programmed. So now we're back to the future. So even if I try to change this now to the current date yesterday, 3/4/2021, and I hit OK, it will seem like it changed, but whoa, there it's back to 2036. So again, I'm overriding or being overridden by that NTP server. And I will change it back here, change it back to once a minute, but it's going to take some time before I get off the naughty list. So let's look and see if I'm still being limited. Yep, I am still being limited. If I look under the R column, there's an L. And right now I see it switched to a K. So that means, hey, I was sending you the kiss of death packet. So eventually I would be able to go back and look at the Wireshark, and I can see that it was sending it every 6 seconds, but eventually that will go back to once a minute, and then I will get off of that rate limited right there. That last packet, I'm still being rate limited, but eventually I would go back and be back on off the naughty list for Christmas, and I would be able to get my time. So that is the demo. That is the killing time demo. So what's interesting is we oftentimes don't do error handling on the time. We have no idea. We've had no buffering. We've had no history, but yet we're easy to propagate time, again, bad time everywhere. So ICS time is so critical. We need to make sure that we're handling the kiss of death scenario. Otherwise, we're just going to be killing time. So, Mr. Conway, my esteemed colleague.
Just one thing I'd like to point out is this, that kind of walkthrough, as we have had the initial running of 612, we kind of got feedback from some of the people in the room last year. And this whole conversation of, hey, kind of closing out towards after our troubleshooting and after our competitions and after everything we're doing in the class to kind of rebuild and recover the process, we'd really love to see kind of a walkthrough start to finish of what information does an adversary need to perform an attack? What does the construction of that attack look like? And then what is the delivery of that? And now that we've built this entire operational environment with OT system monitoring and everything in the classroom, how do we detect it and what actions should we take? So full kind of start to finish lessons learned. And this is one of 4 new things that we've added, kind of walking through this in the class. We call this kissing bear perhaps, or something different other than kiss of death. But we really start looking at how manipulating this controller in the way Jeff just did, and how other systems that are tied into that controller start getting invalid time as well, what that means for the process. And again, just other things that can be done with this. I imagine at some point in time, as we think more evil or more into GridNet wars, how we can use things like NTP and things like this kiss of death packet to specifically trigger and cause some latent logic to execute. So it can be the execution code of something that's been there for some time. Now we want to create a condition that it's been waiting to see that's unique. So thinking of all the direct impacts it can have on a single device, on multi-device, on an entire process, on calculations like velocity and kind of PID tuning, as Jeff walked through, plus your higher level kind of applications as mentioned in the enterprise, and even beyond all of those things as more of a access kind of triggering path for something that's a trusted path, trusted protocol, and it's an event that can be triggered that can bring forward a number of kind of latent capabilities. I think we're going to move to questions. We may be on time.
You are on time, and there's not questions, just a bunch of love. The one question that did come up was about courseware. It was saying, hey, love 612, was super excited to take it, looking forward to seeing it again. But are we also expecting to see a 600 level ICS pen testing course coming?
Absolutely. So there's a couple of things we are very, very interested in bringing to the community and working on them throughout this year. One is kind of picking up from where 612 is, kind of that operational environment, and providing many operational environments for people to develop assessment skills and pen testing skills. And from a local device to an operational environment, and really kind of develop that. The ICS for managers is also one we are keenly interested in creating this year. And we would love to see, even if it's a short course, a ICS specific reverse engineering malware course. Those 3 things would be on my, did we do good this year for the community? And if I can say we created those this year, I think the answer is 100% yes.
Awesome. All right, gentlemen, the other question that came in was around whether this would be relevant to the PTP protocol, if it's replicatable in that.
So you can definitely affect PTP because it starts with that clock. Now there are limits to skewing how far you can skew, but you can definitely go make it chase it. That would be a real interesting one to go do as a demo. So I love I love the question. I love the idea. And I will say this, you guys started with how wonderful this community is. And what's amazing about the people that I get to work with is we're using and doing things that are physically real. And the people who work on this stuff are just incredibly brilliant. And I feel blessed every time questions like that come up. It spurs the creativity in all of us. And so I say a huge thanks to the community that we're part of, and to you guys for hosting. Man, the lineup of folks that you guys got to come, and the people who came here and spoke.
I get to say nice things about you, Jeff, not the other way around. All right.
Yeah. Hey, somebody mute him.
Get him off stage. All right. But there's a couple more questions actually for you, and we got time for it. So does rate limiting happen in a similar way if the source is GPS instead of NTP?
I don't 100% know. I would assume it's how you use it, how you consume it. So that would be my best guess answer.
Depends on your gateway and what you're doing with it.
Yep.
Okay. And then apologies if I missed this, but how did you think of this? Was this like a threat modeling approach, or was this just wild scientist? Jeff's been through some stuff.
Both. So part of it's just wild Jeff been through some stuff, and I've had a weird fascination with time because it was always wrong in plants. And when people wanted to know what was going on, mostly me, is I had no idea because of the time. And so literally over 25 years ago, started digging into like how hard could time be? And that's like, oh my gosh, it's hard. And I'm still trying to figure it out. So it's hard in little embedded devices to get everybody coordinated. And there are really smart people that work on it. But
this is one of those examples. This is one of those examples of going to your process engineer, your instrumentation control person, and saying, how would you take the plant down?
Yeah. And
then they say, well, I've already seen it fail this way, because things aren't configured right, or there's these problems. And then that becomes a potential misuse case. And Jeff is, an encyclopedia of misuse cases as a system integrator that's been in just about every environment that you could think of, and seen a lot of ways that things fail.
Yep. Perfect. All right, gentlemen. Well, thank you very much for your time and effort. Fantastic presentation. Thank you so much.